although the Hungarian railway infrastructure management have in the last few years made considerable progress with the aid of European financial funds, there are a lot to do to make up arrears of work in order that their services may come up to expectations. The goal of rail modernization projects on the main lines, the so-called corridors, is the total renewal of a line section involving the complex rehabilitation of tracks, catenary and signalling. In the signalling area, in the last few years, several large railway stations have been equipped with up-to-date electronic interlocking. The replacement of the old system with electronic interlocking is only one among the possible solutions for signalling reconstruction, but it is extremely expensive. On railway lines, which are not so important and financial resources for their modernization are scant, a partial digitization of existing interlocking systems can be a good solution. Hungarian railways have earned their good reputation for safety with a relay interlocking system which has been operating reliably for decades. The further operation of the more than 300 25 to 45-year-old station interlocking systems is not hampered by the relay units themselves, which were planned to last for 50 years. The main difficulty is the poor state of the traditional push-button control panels and their incapability of being remotely controlled. This film presents an up-to-date railway traffic control system meeting modern requirements of safety and informatics, into the framework of which an electronic control subsystem has been integrated with the traditional relay interlocking system. After a public procurement procedure, Hungarian State Railways commissioned ProLan Incorporated to install a traffic control system on certain lines of the Szeged Regional Directorate, covering 13 stations to be remote controlled and 39 stations to be monitored only. One of the main goals of MAV is to save labour, which can release funds for development and also cut operational costs on the given lines. The remote control of 13 station interlocking systems is carried out from the Kiskörös, Kiskunfélegyháza and Szeged remote control centres. With stations without traffic staff, other remote-controlled and monitored subsystems had to be put in. Among these subsystems, the catenary remote control, the so-called FET system in Hungarian, is of primary importance because it enables 4 120 per 25 kilovolt transformer substations, 11 supply and disconnecting neutral overhead wire sections and switch fields of 15 railway stations to be controlled from the Szeged centre. A smaller but key part of the remote control signalling system is the fire protection and security subsystem. Point heating and station lighting are also monitored by the FET. For the remote control of the station interlocking system, the operation of CTC FET systems and passenger information setups, 3 independent fiber optic-based bypassable 2 data transmission paths with a speed of 2 megabits per second have been made available as part of the WAN SDH communication system of Hungarian Railways. An integral part of the whole system is the automatic public address audio subsystem based on the current traffic data of the CTCs, which can carry live information as well. Basic elements of our railway automatization and renewal projects are the complex hardware and software of the so-called electronic control desk, or ELPULT in Hungarian. The main function of the electronic control desk is the control of the relay-based station interlocking system with electronic and computerized tools. A condition of putting the electronic control desk into operation is the full remote controllability of the station interlocking system. In this particular case, the D55 station interlocking system had to be complemented with a relay circuit in control of the switchover between remote and local modes of operation, and also be made responsible for higher safety standards. As a matter of course, each function of a traditional control panel is performed by the electronic control desk. But not only these functions. Numerous other services have been made available with computerization, like for example logging, storage functions, automatic functions, and also the monitoring of other stations' subsystems. The application of the electronic control desk cannot compromise the safety of the relay system, nor can it alter the availability of its controls. Therefore, the architecture of the electronic control desk has had to fulfill the requirements of safety, functionality, and availability at the same time. On account of their different types of function and their different locations, we can make a distinction between two levels of the electronic control desk. The terminal level, which is a modularly built industrial microcomputer based on the Profield B system of Prolan Incorporated. Located in the relay room and connected to the iPro interface of the relay interlocking system, it lends itself to the primary processing of field information and its transmission to the WAN network. In order to fulfill safety requirements, the handling of indications has been made redundant inside the terminal, which means that one indication generates two input signals, a normal and an inverse one, at the input of the terminal. To output a command, two terminal control channels must be operated simultaneously but obversely. It means the fulfillment of a logical AND condition and securing the supply voltage of the C-type relay responsible for the execution of the command. The CTC level, which is a large capacity server computer with a 1-to-4 screen. The CTC level is linked to the terminal level via the WAN network and is also responsible for the man-machine interface tasks of electronic control desk system. At both levels of the system, the availability requirements are fulfilled by a complete hot standby structure. The development and installation of the whole system has been carried out in keeping with the European standards valid for railway safety systems. The safety case of the system has been certified and assessed by the Department of Control and Transport Automation of the Budapest University of Technology and Economics. The final permission for use was issued in December 2009 by the Hungarian National Transport Authority. The ELPUD, our electronic control desk, is an electronic MMI for the signalman, whose controls consist of a monitor, a keyboard and a mouse. Railway objects are indicated as graphic symbols on the MMI. The actual statuses of the track layout and those of the railway objects can be displayed on the so-called magnifier view. Any area of the monitor can be magnified. Since the ECD systems of neighboring stations are linked to the same common network and they transmit all information to one another, a line section in itself or each station of a whole railway line can be viewed on screen. The bottom band of the screen indicates the latest events of the general event log. A filter with easy and fast functions helps users to choose a discretionary lineup of views. In addition to the visual indications, there are audio signals to draw the signalman's attention to any important event. Following the audio indication, a textual summary of the given disturbance can be read in the disturbance log with its acknowledgement and timestamp logged as well. The fault register is a special railway document. It logs all failures and registers them for troubleshooting and stores all features of the given failure with a timestamp and notes by the mechanic. The signalman's most important logbook is the traffic logbook, which registers all relevant events of the actual train traffic. The lines of this logbook are automatically generated, but manual typing is possible as well. Registered maneuvers are logged in a juridical recorder. Not only the special, the so-called registered maneuvers, but all normal ones are logged too. The point of time another signalman enters into service is also registered. At the end, the logbook of operational mode changes is continuously brought up to date. The program of the electronic control desk orders train numbers to each track occupation with the aid of the signalman. The official timetable is stored in its memory. The system follows train numbers automatically, which is very useful for the signalman. If no train number has been ordered by the signalman to a departing train, the system automatically generates a fictitious number, which the signalman changes to be listed as the appropriate one as soon as possible. The program is prepared to handle the case of more than one train standing on the same track. Trains are assigned several characteristic features which can be changed until their arrival. As train data, these features are stored, handled, and can also be displayed. Train movements can be followed on screen. Among other operations, individual point setting is one of the most important maneuvers. If a point has been selected by the mouse on the MMI, the point setting operation can be chosen from the roll-down menu, and it will be executed by the interlocking system, which in turn will control the point machine. The operation of point setting can be followed on screen. Train movements are controlled by signals. Train and shunting routes can be set if the starting or target point of the route is selected. The so-called first locking of the route is indicated by a green line on the screen. Signal setting can be chosen from a roll-down menu as well. The derailleur provides safety for train movements. Derailleurs equipped with point machines can be set from the electronic control desk too. The Scotch block barrier protects train and shunting movements, wagons standing on and rolling from industrial sidings. Level crossings are protected by warning signals and barriers. There are different maneuvers and indications on the electronic control desk for station level crossings, only with warning lights, and for level crossings with additional barriers. Closing commands initiated by the train and controlled manually by the signalman are indicated with different colors on the MMI. The power supply of the station interlocking system is monitored and switched off in case of emergency by the electronic control desk as well. Programmed operational modes make the signalman's activities easier. It means that certain pre-programmed commands will be issued depending on the actual train movement without any intervention by the signalman. In case of a passing mode, an open line direction will be set first. Then the system is waiting for the train. If it enters a predefined section, this time in block section T2, the entry route will be set automatically. The actual state of the automatic route setting and commands issued are indicated on screen. Of course, these commands are registered in a juridical recorder together with the designation of the automatic operational mode. These automatic route setting functions can be prepared for any traffic situation. Now the passing and crossing modes have been permitted. Of course, the public address system is controlled by the train movements, therefore passengers can be notified of any delay. In the beautiful old station building of Szeged, renovated in 2005-2006, not only the central traffic control is located, but on it the actual statuses of 41 stations in the 330-kilometer long railway area are indicated too. The old CTC of Szeged had been put into operation by MMG Automatics in 1990, and it remained operational up to February 2009. The new control system reads the station statuses from 3 sources, that is, 13 stations along a 100-kilometre long railway line give data via the new RTUs. 5 stations are connected to another system, and the remaining 23 stations are operated with the old Nuovo Pignone P6008 type RTUs. Therefore, in the Szeged CTC, not only a remote-controlled workstation with its hot standby MMI has been installed, but also a workstation for all traffic dispatchers in the whole area working together. The traffic dispatchers prepare a daily plan based on the timetable in force and on the data of operative trains travelling on the given day, and make their traffic organisation decisions on the passing and crossing of trains in keeping with the actual train paths. In order to get an overview of the whole monitored network, dispatchers are provided with a projected picture too. A reduced package of CTC services is available at 7 key stations of the area, where they have so-called overview terminals. Real-time visual information on track occupation and other element statuses serve as useful support for the signalmen working on these central stations. In a room adjacent to the CTC centre, the catenary remote control workstations are located. Beyond the above-mentioned 13 CTC stations, 2 further stations, disconnectors of 7 cut-off and 4 supply-neutral sections, and 4 transformer substations can be remotely controlled from the catenary control centre. The lighting and point heating of these 13 unmanned stations are governed from the catenary control centre as well. Server computers, uninterrupted power supply units with duplicated feeding, and terminals of the communication systems are located in the air-conditioned server room. The central equipment of the communication and public address system has been installed in the air-conditioned telecommunications room. The Szeged Railway CTC was built in 18 months by ProLan Incorporated and its subcontractors. A 6-month-long trial run and the period thereafter give evidence of the fulfillment of the investment targets. The efficiency of rail transport has been increased with safety requirements also fully met. Approximately 70 persons from the stations have been released as planned at the beginning of the investment. ProLan Incorporated, enriched by experience gained during the Szeged project, is ready to play another key role in similar future projects.